Okay, students, so we will start in next 5 minutes. We will wait for other students to join. We will start at 6:05. We'll wait for other students to join. देवीलाल, रूम पे हो? अरे कुछ नहीं, आईपैड चाहिए था, मेरा आईपैड काम नहीं कर रहा है। मैं शायद इसको कॉल करता हूँ, उसका कॉल लग नहीं रहा था राजेंद्र का। ओके, ऐसा है, ठीक है ठीक है। ओके ठीक है, हाँ, बाय। Yeah, so actually there is a problem while connecting my iPad with the laptop. It used to connect earlier, but now I'm facing issues. So yeah, so Zua, am I pronouncing correctly?
Yes, sir.
Yeah, so yeah, so it's, just to ask you, could you please introduce yourself? Like, tell me about your studies and all, so that we can start the session.
Uh,
Mhm. Okay. Okay, nice. I'll just ask my friend if I can get the iPad from him so that I can connect it here. Yeah. Yeah. Yes, sorry for the delay. Actually, there was a problem with the iPad. Now that I got the connection back, so we will start the session. So good afternoon, good evening, everyone. I'm Prashil. I'm a PMRF at IIT Bombay, and here we are learning advanced thermodynamics and molecular simulations. Right? Okay. So the name of the subject is advanced thermodynamics and molecular simulation. Correct? So the name itself tells it is an advanced level course, right? Where we will be studying the thermodynamics, right? Thermodynamics is something that we have already covered, we have already learned in our uh, undergraduate, correct? So we are adding something advanced into it, right? We will add something advanced here, and using the statistical framework, we will be developing a framework to study systems systems at molecular length scale, to study these systems at molecular length scale. Okay. Yes. Right. So this is our week 1. In this week we have studied basics of probability. If you just go through those lectures, right, and use this probabilistic understanding in thermodynamics, right? Thermodynamics. So what happens, these simple probability concepts can be applied, right, to develop a methodology that can be used to study the systems at molecular length scales. And there we will be talking about, okay, there are multiple thermodynamic quantities, for example, internal energy U, then there is entropy and multiple other properties, and this can be related to macroscopic phenomena, can be related to macroscopic phenomena, correct? So whatever thermodynamics that you have studied in undergrad, again we will be just applying some mathematical framework to that to develop a model and solve the equations, solve the model that we have developed, right, to understand the system properties, correct? So in a simple sense, if I want to go and tell, you have started learning some language, could be your mother tongue or for example English, right? So what you do, you start speaking those things, right? Speaking is something that is important. And then when you go to school, you apply grammar, you understand what is the grammar behind when to use what, right? Those things we understand in school. So this is similar to that. We studied thermodynamics at undergraduate level, and now we are developing a grammar. We are understanding the grammar behind it using mathematics, right? Using mathematics. So this is the basics that we wanted to understand over here, right? We covered multiple things. For example, what are the different laws of thermodynamics, that is again basic, right? But those basics can be understood in terms of mathematics, and in statistical mechanics we can apply some advanced concept, right, to understand the properties of system. Okay, then we have talked about something which is very important, internal energy, which is what we have studied in thermodynamics whenever we start. As discussed in the class, what we did there, right, there we said, okay, internal energy is something that is composed of all sort of energies that are associated with the system. For example, I have a beaker, and in that beaker I am taking water, right? So these water molecules will be having some attraction, some repulsive interactions among them, right? And because of which we get some quantity called as internal energy, that tells you the capacity of that system to do the work, and this we model using interaction energies, right? For example, between two molecules there will be some interaction. What sort of interaction there could be? Could be attractive or repulsive, right? And depending on that, the molecule can go away from each other or they come together. And generally these interactions are van der Waals interactions, and then there is something called as electrostatic interactions. Then there are ionic interactions, there are dipole interactions, right? So in this beaker, what I took water, and because of which water will be having interactions. For example, van der Waals interactions, which is because of the um, electrons, right, that are present in the atom, correct? So there is a fluctuating dipole there, and because of which there is some attraction between molecules, so that will be obviously there. But you must have studied along with that there are something called as hydrogen bond, which is present in the water. So all sort of hydrogen bonds which are present, if you sum their interaction energies, if you sum their energies, you will get something called as interaction energy or internal energy of the system. When we go to macroscopic scale, we study, okay, energy can be broken down into two parts: potential energy plus kinetic energy. Here potential energy denotes it is the energy because of the, because of what? This is because of, for example, this is a ball which is here and gravity is acting on it, so this is because of the height, distance, that gravitational force that is acting, and because of which there is corresponding energy. And if the ball is moving, then it is having some velocity because of which there is a kinetic energy. Similarly, when we go at micro scale, or again deeper nanoscale, where the dimensions of the fundamental particle that are present in the system, for example atom we have or electron we have, those are in angstrom scales, right? And because of which you see that multiple atoms are interacting, right? And there will be attractive or repulsive interactions among them, and some of those interaction energies will give you the potential energy. And you know that these particles will move, right? Because of the thermal motions, because of the thermal motions. And then you will be having velocity. So these energies are functions of height, and these are the velocities, correct? And it will give you the internal energy of the system. So here we will be studying the systems at angstrom or nanometer scale, where we have atoms or molecules, correct? Atoms or molecule. For example, if I draw water, right, H2O. So this is my molecule, right? Similar to that, there will be n number of molecules which will be interacting among, and because of which you will get the energy of the systems, correct? And in the class it was mentioned that okay, when we are studying these systems, we are at the interface of we are at the interface of two things: classical mechanics and quantum mechanics, right? In classical mechanics, energy is a continuous function, while in quantum mechanics, when we see here, it's not continuous, it's discrete. So energy always comes in discrete package. So if I'm having an atom or electron, whichever is the fundamental particle, you will find that it may have energy 1 quanta. For example, epsilon here I'm representing as a quanta of energy, or 5 quanta, right? So it is coming in discrete package, and the fundamental unit here is the quanta, and always energy will be in terms of quanta. So you can see the electrons are present at different energy levels, right? Epsilon, 2 epsilon, 3 epsilon, right? So this is how the energy is distributed in the quantum systems, whereas in the classical it is continuous. Why it is continuous? It is because of the mass associated with the molecules that we study in these systems. Here the mass will be in kg or gram, length will be in meters, right? And time is in seconds. But when you go at the quantum scale, you will see that the mass is very less, right? And it is atomic units, AMU, correct? Atomic mass unit. Then you have length, which is in angstrom or nanometer, as I said earlier, and time will be in nanoseconds or microseconds. Most probably it will be in nanoseconds, correct? So at this scale we are working here in quantum mechanics. So because of the mass, majorly because of the mass, the difference comes, and that we will be studying using something called as de Broglie wavelength, where it says okay, for a bigger mass, right, for a bigger mass, the movement will be very less, right? The movement will be very less, and the de Broglie wavelength that we will calculate, it will tell whether that will exert these quantum mechanical motions or classical mechanical motions, right? So when we plot this particle in a box, you will see, with respect to change in the quantum number, change in the quantum number, this sort of waves are being formed, right? This basically tells you probability of finding a particle in a box of length 0 to L. But as the mass increases, you will find that we're going to prove these energies will be becoming like this. So you can see earlier there was only one this curve. Now we have multiple overlapping curves, and that's why energy is continuous. Energy is continuous. Okay. So then we related these things with the entropy, right? So first concept that we talked is energy, and second concept that we talked is entropy. First is energy, second is entropy. First is energy, second is entropy. What is energy? Energy, that's what we studied. It's the sum of all sort of associated energies that are present in the system. All sort of energy that are associated in the system. And what is entropy? Just like what we saw here, how energy is distributed. How energy is distributed among particles, or I could say in the system. So distribution of energy is something that is related over here. Distribution of energy, that is something which is related over here. So this talks about the distribution of energy. Now we have said one term, that is distribution, how it is distribution, and based on that distribution you will be having a probability of particle staying in that particular energy state, correct? So whenever distribution comes, it is associated with the probability, and when we understand the probabilities, right, we can use these concepts to develop theories that could be used to study the systems, correct? For example, I am having a coin. How many outputs I can get here? I can get head or tail. Head or tail. If I am having two coins, then what are the outputs? Head on one, head on second coin, head tail or tail head, and third is tail tail. Tail head, correct? So can you see here what has happened? There were only two outputs, each of which are having zero point 0.5 is the probability. Now because of the increased number of coins, I am having probability over here is 1 by 4, 2 by 4, and again it is 1 by 4. So when you plot the distribution, right, you see you have more number of outputs that are possible. Similarly, if I am having more number of coins, I will be having more outputs. If I consider, okay, how, for example, here how many heads are there? Only, here there are two heads, that means fraction of x equals to 1. fraction of heads is equals to 1. Yes, so we were talking about the advanced thermodynamics. How can we use uh, the concept of statistics into thermodynamics, right? To understand the systems at molecular length and time scale. And whenever it comes to statistics, it is always associated with the probabilities, and that's why we are learning how these concepts can be applied. Yeah. Okay. Yeah. So are you guys able to listen to me? Hello? Hello?
Hello, hello, hello.
Yes. Hello? Yeah. So I believe there is no echo issue now. Yeah, so I'll just introduce myself. I have started at 6 o'clock, and just to inform you, I'm from IIT Bombay, and I do molecular dynamic simulations and Monte Carlo simulations to understand the properties of systems. And here we will be studying those concepts, right? For example, the methodology, that is what is statistical mechanics, to understand the systems at molecular length and time scales. Okay, so this is our first class, and this is our first live interaction session. So let me just ask, okay, the students to introduce and let me know anything that has made interest to you in this subject. So Vishal, can you start? Hello. Okay, actually I cannot hear. So we were talking about advanced thermodynamics, and majorly we were working on two things. First thing is entropy, or you can say first thing is energy and second thing is entropy. So energy is something that we have studied in undergraduate. It's the energy, that means it is the capacity to do the work, right? Yeah. So Bishal, can you speak now? Yeah, yeah. So could you please introduce yourself? Ah, okay, nice. What about Anaga? Okay, from IIT Indore, BTech third year. Okay. So we were talking about two things, energy and entropy, right? Energy is something that we have studied in undergrad, and we know that it is the capacity to do the work. Capacity to do the work, right? Whenever I'm having a ball, right, over here, for example, it has some height, and because of which it has some potential energy, and when it moves, right, it will be having some velocity. So there are two things, one is height and second is velocity. So because of this height, it will be having some energy, for example, which is a function of height, and some energy which is a function of velocity, right? And that's why we are combining these two to get the total energy, that is potential energy plus kinetic energy. Here when we look at, we just see, okay, there is some mass, and because of that mass there is some associated um potential energy, and when it moves it will be having some kinetic energy. But when we go deeper and deeper and deeper into molecular length scale, we see that the mass decreases to a very small number. Earlier we were having, for example, a ball which is over here, right? We see molecule, for example, it could be a polymer, right? And polymer, it will be having some mass in daltons, right? Or again, when we go, instead of going into the polymer, for example, I have some alkane molecule which is having structure like this, correct? So this is carbon carbon, and we can represent this. So here we see that we have some atoms which are connected here via some bond, and because of which there will be some attraction between atoms or repulsion between atoms, right? And they may come closer, they may go away, and that we refer to as energy of that particular molecule. As we took an example, it could be a polymer. Simplest example if I want to take, then I'm having a gas which is present in a container. So this is my container. It has some gas particle, could be ideal gas particles. I have drawn some volume over here, right? But then these are particles which are point particles, and they are not having any volume. But yes, these particles, gas particles, are there in the box. Now, what is the simplest interaction that is present between two atoms? For example, I am having an atom over here and there is another atom. The simplest interaction that we could imagine is no interactions, right? No interactions between these two. Even if I am change this molecule's position, the other particle is not affecting. That means there is no interaction between those two particles. That is the simplest interaction that we can assume. What is some other types of interaction? We can say, for example, first I explained that is no interaction. If I change the distance, that is d, between these two atoms, there is no change in the energy. That is the simplest interactions. Second interaction could be Up to particular distance there is no interaction between these two particle, but suddenly it comes and sticks. So this sort of interactions are called as a combination of attractive and repulsive, right? So this sort of interactions are called as steep hard spear interaction. That means there is no interaction up to certain distance, and whenever they comes beyond certain distance there will be infinite energy. This sort of interactions called as hard spear interactions. Or you can see this sort of interactions where you can see the interaction energies are zero at longer distance, and as two atoms come closer there will be some attraction which will decrease up to certain distance, and since atom cannot penetrate, right, there will be again increase in the energy. So this is the interaction energy between two atoms that we are modeling over here, right? So because these atoms attract each other or repel each other, right, there will be an energy that is associated with it, and that energy we are calling it as a internal energy. And as these atoms moves, right, there will be velocity associated, and because of which I am having kinetic energy. So I did these things for one atom or two atoms. Similarly, I'll sum it over all the atoms that are present into the system, and there will be total energy of the system. Again, you can see it's the same, which is the sum of potential plus kinetic energy. Potential plus kinetic energy, right? When I'm saying okay, it is the energy, right? It is a quantity, and it has been distributed into the fundamental particles of that system. For example, if I am having a system where I have molecules, right, which are there and they are atoms, and because of which my fundamental particle is atom, right? If I go one level deeper and see inside that atom there are electrons, protons and everything, right? So because of which there will be some interactions, right? At that level, there will be some associated energy among that, and we model it at quantum level, right, where we have discrete packets of energy, so at different level there are certain energies. We need to sum over all these energies to get the internal energy, right? And based on the velocities we will be getting kinetic energy. Now these energies are distributed, as I said, and those distribution, how it is distributed, that will corresponds to the entropy. For example, I have three particles. I am giving total interaction energy as 3 epsilon. How can I distribute these things? I can give 3 epsilon to first particle, 0 epsilon to other particle, again 0 epsilon to the third particle, or I can give 1 epsilon, 1 epsilon, 1 epsilon, and I can have whatever possibilities that I can do. Then you have to calculate something called as the ways of distribution that we studied in the class, right? W is the ways of distribution, correct? Similar to this, we had a formula, right, which tells you if I am distributing the energy among the particles, if I distribute the energy among the particles, what is the W? What is that W, right? And that W will give you, okay, if it is maximum value, that means it is the most probable state. It is the most probable state. Based on the probability, we can predict that. And we have to maximize that W, right, to get the entropy of the system, which is S is equals to Kb ln W. In the lecture, the detailed derivation and detailed things are there. I'm just telling you superficially because this is our first class, and from the next class onwards, we will be solving the assignment problems. Correct? So this W appears over here, which has no unit. Correct? Which has no unit. If you multiply by Kb, it will be of the unit energy per Kelvin, and this W is again related to S, that is our entropy, which is an additive property. So as we see in the class, I am having two systems. Here there are some atoms, here there are some atoms. I am distributing energy here, right? W1 are the number of ways over here, W2 are the number of ways over here. In a simple example, we will just take coin and understand how this equation came. If I am having only one coin, I'll be having only one probability, head or tail, both of which are having equal probability. But if I have two coins, then total number of outputs are 4. Here it is 2, head or tail head and tail tail. So what has happened? We did two things. I have coin 1, coin 2, head, head and head tail. So what we did just now, correct? This into this, head into tail. Then we have other combination, that is tail into head and tail into tail. So what did you observe? If I'm having two systems and if I'm having one system, what is the difference? We see that the number of outputs has changed, right? Number of outputs are have changed. Whatever number of outputs were there for one systems, if you multiply with other system, right, the total number of ways, here in second system we have 4 and in first system we had only 2. So by breaking that system into two, or if I'm having multiple systems, we have increased the number of outputs. We have increased the number of outputs. That means what has happened? W has increased, right? W for first system is equals to 2 and W for second system is 2 into 2. That means output of this system, the first one, multiply by output of second system, that means this multiplication, and because of which it is 4. That means what has happened? W has multiplied, right? So total W is equal to W1 into W2. So this is a multiplicative quantity, right? Multiplicative quantity, and it is related to entropy, which is an additive quantity. If I increase the size of the system, entropy doubles, right? It is an extensive property. S is equals to S1 plus S2. So what is that relation which will relate these things to that we wanted to study, and hence the relation that came out, that was S is equal to Kb ln W. You can see total S is equals to ln W1 plus ln W2, correct? That means S is equals to S1 plus S2, which satisfies first condition. Second condition is, here it is ln W, and W is equals to W1 plus W1 into W2, which also satisfy this multiplicative term. That's what we have studied using coin example. So it is the only equation that gives you this quantity. And then we saw, okay, this S which is dependent on W, right? And using the second law, we know that as that is entropy, it should keep on increasing, and whichever is having higher entropy, that is the one which is the final state, correct? And ultimately we are going to reach an equilibrium. So what is the fundamental principle is to increase S. That means we need to increase W, that is the number of ways in which we can distribute the energy, correct? And we use this concept to derive multiple properties in the coming lectures, where we'll be maximizing number of ways of energy distribution, and we will come up with multiple properties. For example, dg is equals to kb ln q, or df, which is Helmholtz free energy, which is equals to kbt ln q, correct? All those sort of relations that we will be studying in future will be coming based on the maximization of this W. Apart from this, what we saw, it was the relation where we use statistical mechanics, right? We use statistical mechanics to derive the equation of state, right? That we saw in the class. There we derived, okay, internal energy, PV is equals to nRT, this equation, right? It also came from the principle of StatMech. There are number of ways to prove this equation, and one of the ways to use statistical mechanics, where we saw, okay, I have a system which is having ideal gas particles, right? They are not interacting with each other, so total energy is equals to potential energy plus kinetic energy. Potential energy is equal to 0, so total energy is kinetic energy, and then we use a number of assumptions. For example, when the atoms are moving, they have some velocity because of which it has some kinetic energy, right? And we derived this equation, PV is equals to NKT, right? PV is equals to NKT, purely based on the probability and statistical mechanical approach. So based on these and the probabilities that we studied in our undergraduate, right, we took some of the examples, and those examples again were very easy, and those concepts and similar questions are also given in assignment. I hope you can solve those things, solutions of which we will be discussing in the class, right? One of the major thing that was there in the class is how the distribution changes with n, that is number of particles, or with a simple example we say with the points. Three important observations that we made, right? What were those? When you have two coins, when you have four coins, when you have eight coins or something, we saw that the probability of having head or tail, this could be fraction of head or fraction of tails, other, because it is a binomial distribution, so that doesn't matter which is there on x-axis. And here probability of having head or tail, right? One of the major thing that we saw is, as I increase the number of coins, this is fraction of heads is equals to 1, fraction of heads equal to 0, and fraction, this is a probability. We saw that the curve starts to become like this, and as you increase again n, so for example n is equals to 2, n is equals to some higher value, and as I increase the value of n, you will see that distribution will become like this. So what is happening, what were the observations? We saw that as n increases, as n increases, the probability of having any fraction of head, right, decreases. Probability of, that is what is we are seeing in this curve, right? Probability of having any fraction of it, any value that is present on x axis has decreased. Correct? Probability has decreased. What has happened, second thing is, you see the probability of having these extreme values where I have the fractional fraction of heads away from zero point 0.5 has decreased. Has decreased, right? That means probability of having fraction of head 0.45 or fraction zero point 0.3, obviously the probability of having this has increased than this, right? We are more or less closer to the equal distribution, which is what is the principle of equilibrium. So in all these distributions, if you just divide everything by the highest value in that distribution, right, highest value of probability in that distribution, you will see that the of having probability of having distribution close to the center value has increased. That means the extreme points are having lesser and lesser probability. That is what is the principle of large numbers. Principle of large numbers, that means when we are increasing the number of particles in the system, number of coins in the system, the probability of having central distribution, that is what is central limit theorem, right? It says that probability of having the central value increases. What is its importance? Its importance is whenever we want to study these systems, right, which is having large number of outputs. For example, we can have fraction of heads varying from different values, right? So we can just ignore these values which are at the extreme in the integration, and we can just study these systems, because in real life it is difficult to study all the fractions. That's why we focus on one which is having highest probability and its surrounding, its surrounding. Lastly, we also saw a chemical reaction, and we use completely probabilistic way to understand the concepts of equilibrium constant, right? Equilibrium constants, and we Notice that, okay, equilibrium means equilibrium means something that maximizes the W, and that was came out to be 1, right? Maximization of W. So in the class, if you have not understood any concept, we can elaborate on that and we can discuss that thing in rest of the time. We thought of discussing the assignment questions here itself, but then there is a deadline beyond. After that only I can discuss those in class. So in this class we are not discussing the assignment questions. So if you have any doubts in the lectures that you studied in week 1, we can discuss in more in the rest of the time.